I have the Palmer Penguins data set here, which I'm going to use for a quick demonstration of simple linear regression. The first thing you want to do, if you haven't done so already, is to produce a scatter plot just to double check that the relationship is linear. There's a few different ways to do this. This example, I'll go to regression, classical correlation. When we get to simple linear regression, I am going to use flipper length to predict body mass. And the way that JASP works is the first variable you put in will be on the y-axis and the second variable will be on the x-axis. Select scatter plots, and here's our scatter plot. We can see that there's a very strong positive linear correlation between these two variables. Because the relationship is linear in nature, we can use simple linear regression to make this prediction. To get our regression model, I'll go to regression, classical linear regression. I want to predict body mass. The variable that's being predicted is the dependent variable. It goes in the top box. And the independent variable, so the predictor variable, is flipper length, which JASP calls a covariate. So again, I'm using flipper length to predict body mass in this model. If we zoom in to our output, the first table you get, you see there's actually two models here. Ignore the model that's labeled HO. That's the null model. That model just contains an intercept. This is what we're going to compare our model to. What JASP is essentially doing, or when we do a hypothesis test, what's really going on in the background is we're saying, is our model, which has an independent variable, better than the model that doesn't have this independent variable? So you can just ignore all of the rows that say model HO. What we're checking here is the alternative model H1, which contains our independent variable of flipper length. In this first table, what you're really interested in here is R squared. That's your coefficient of determination. It's the measure of effect size that's used with simple linear regression. The second table we get is an ANOVA source table. This is testing for the statistical significance of the whole model. With simple linear regression, the only variable in our model is the one independent variable. So this is actually redundant with the t-test statistic that we'll see in a second. You have the option with simple linear regression of reporting the F statistic with these degrees of freedom and this p-value, or reporting the t-test statistic for the slope in the next table. So one option for reporting the statistical significance of this model is to say that F with 1 and 340 degrees of freedom equals 1070.745, p less than 0.001. Because the p-value is less than the standard 0.05 alpha level, this model is statistically significant. Another way to look at this is to use the values from the coefficients table at the bottom. This table gives you some extra information in addition to that statistical significance. Again, ignore the row that says HO. You're going to focus on the model labeled H1. This is our y-intercept, and then this is the slope. We can put these values together to get our regression model. The predicted body mass is equal to negative 5,780.831 plus 49.686 times the flipper length. So if we wanted to use a penguin's flipper length to predict their body mass, that's the equation that we would plug their flipper length into to get their predicted body mass. Last thing I'll show you is the values that can be used in this table to test for the statistical significance of the slope. And those are the two values at the end here. This is the t-test statistic and the p-value for our slope. Again, the p-value is less than the 0.05 alpha level, so the slope is statistically significant. That means that the slope for flipper length is significantly different from 0. We can use flipper length to predict body mass in the population.